In a world where images exist, and they need to be transmitted, one team of 3 will bring conventional techniques to the next level and send 100 kilobytes of data where only 7.8 have gone before. This is no kill like overkill.
To compress our image before modulation, we used wavelets to decompose it into multiple detail levels. With this representation, it was easier to remove small details that don't have much of an effect on the final image, thus allowing us to greatly reduce data size in preparation for transmission. Additionally, the image can be partially reconstructed from the moment the low-resolution components are received.
After compression, the image data is packetized, appended with CRC, and transmitted. Our modulation scheme is audio FSK with 1500 and 3100 Hz tones at 2800 baud. This is a 133% improvement in baud rate over the baseline modulation scheme. In case some packets get corrupted, we created a graphical user interface in order to allow resending them. To avoid wasting time on transmitter ramp-up and PLL locking, our transmitter program continuously sends synchronization bytes when no packets are available. This allows any resent packets to go out immediately.
Our philosophy has always been, you're not doing a proper project unless you're going to get written into a rulebook. We took that to heart in this project. 5 times the balfanes, 5 times the bits, and 5 times the fun. But 5 times the radios isn't fun if you have to use half of them for receive. So we have these handy-dandy RTL SDRs with up to 2.4 MHz of spectrum. To demodulate each FM channel, we applied a frequency selective filter over the band, then use a stock discriminator algorithm. Once we have audio samples, we then pass those through a filter bank, one for each audio FSK frequency. Taking the difference of the filtered signals results produce a positive-negative signal corresponding to zeros and ones. Of course, while this processing is trivial for one channel, it quickly bogs down even the most powerful CPU when doing 5 simultaneous decodes. A lot of effort was spent on making the system as efficient as possible, from doing filtering solely in the FFT domain to utilizing multiple cores.
Some of the screenshots shown are from our visualization program, which we implemented to help with debugging. By looking at the eye diagrams, we can tell which channels are being received successfully and tune the baud rate to trade off speed and bit error rate. The sample points for the PLL are plotted on the demodulated waveforms. The spectrogram shows us the relative power of the transmitters and which radios are keyed but not transmitting. This visualizer is integrated to a demodulator and runs in real time, using PyQt graph for GPU accelerated plotting.
Unfortunately, 5 times the radios also meant 5 times the bugs. A lot of time was spent on debugging hardware to get things working properly. Some were quite obvious, like radio jacks that didn't work, and broken wires in the balfane interfaces. Some weren't, like RF interference branding out the USB hub, or the whole laptop.
But the bugs were no match for our elite programming skills, and in the end, only clean images came through. At 5 times the bitrate, they were of pretty good quality. This received image of Crater Lake was about 100 kilobytes and is almost indistinguishable from the original. Some images, like this, were even able to be compressed losslessly, allowing perfect reconstruction on the receiving end.
We presented a system for sending images over multiple FM channels with commodity hardware.
Opportunities for extension include transmitting real-time video, a single radio automatic retransmit request back channel, radio modifications, and more. Our project has no qualms about polluting the airwaves with multiple channels of balfane splatter modulation. But what it lacks in any sort of precise control of emission, it makes up for in quality of images.
Thanks for watching.